There we go. Everyone can see that okay? Okay. Good morning from my end of the world. My name is Casey Wright, and I am zooming in from Indianapolis, Indiana. So it is the bright and early hour of 6 o'clock in the morning. So I will try to get up to speed with you all. I am so excited to be here and to be in conversation with Carrie. Carrie, do you want to unmute and just introduce yourself so people can hear you?
Good morning. Oh, that didn't sound very good. I'm Dr. Carrie Sapalo, currently in New York City this morning. However, I reside in New Jersey, and I'm looking forward to the presentation this morning.
Thanks, Carrie. All right, so we're going to be speaking about beyond workarounds and mitigation, demystifying chemistry laboratory instruction for blind and vision impaired students. And I also dropped a link in the chat to the slides document in case you would like to follow along at your own pace. Okay, so before we jump into the details of our talk today, I want to note that the language around disability is constantly evolving and nuanced based on the communities of disabled folks we're talking about. I'm going to be using identity first language, such as visually impaired students, instead of person first language. I do so in adherence to the social model of disability, which takes disabilities to be produced by barriers in society and in the environment. And Carrie also prefers this language as well. So I'm going to be speaking about considerations for accessibility and inclusion in our online laboratory environments. And then I'm going to hand it over to Carrie to speak about the in-person lab. So it's no secret that the use of and the need for online laboratory learning environments has increased exponentially in the last several years with the COVID-19 pandemic. And just overall with increasing need for flexibility from our students. And so what I've put on the slide here is a few screen grabs from some of these online laboratory environments. Some are more oriented towards simulating the laboratory environments that we would have in our in-person lab, or leveraging the flexibility of the online platform to be able to depict things on the molecular level. And so with this, we really need to be considering how accessible are these environments. And so what I'm going to be sharing with you today in talking about online lab accessibility is an intervention we did in our course for health science and agriculture students when I was working at Purdue University. And the details of that are in a recent publication in the Journal of Chemical Education that's on the bottom of the slide here. So like others, as we were trying to figure out what were we going to do when we shifted to online laboratories due to COVID-19, we decided that we needed to fill in gaps that were left in our hands-on skill development labs with the online simulations that are provided by the Beyond Labs environment. So there's an image of that on your screen here, of what the general chemistry lab looks like in Beyond Labs. It's kind of your generic bench top that's got a whole bunch of stuff on it, ring stand and a whole set of chemicals in a storeroom beyond that. And so students can work in this 2D lab environment to do some of the experiments that they might get to do in person labs and some other experiments that they wouldn't be able to do otherwise. And so, did I miss my? Oh, and so when we did so, we were presented with a unique challenge of figuring out how to support students who have color vision deficiencies or color blindness. Because our students were working on their own in this online laboratory environment. And typically students who had color vision deficiencies would be like supported by their peers in the lab of kind of using somebody else's eyes. And that was not the case once they were working on their own at home. And so for those less familiar, color vision deficiency or color blindness is a disability that produces confusion around the perception of different colors. It can take on the form of what is medically known as deuteranopia, which is then commonly known as red-green color blindness. Tritanopia is blue-yellow color blindness. And then in more rare cases, you can have achromatopsia, which is when only black, white, and shades of gray are seen. And based on studies of color vision deficiency in the general population, if we have an enrollment of about 1,000 students, like we did in our course at Purdue, if, just kind of rough and dirty numbers of if we have 500 male students and 500 female students, then it's likely that we have about 50 male and 4 female students that might be color vision deficient. And so the important thing to note about this is that those often go unreported. And so every once in a while, we'll have a student who comes up and says, hey, I can't do this titration because I can't see the color. But often they're just not even noting that, it can be particularly a problem, as we know in chemistry, because a lot of the observational work that we do in our general chemistry labs has to do with color. And so what we did was to try to make our online lab more accessible to these students was we adopted an app technology called the Colorblind Pale app. It's a smartphone-based app that is also available for Mac OS, so you can use it on your computer if you have a Mac. And what users can do is take a screen capture and center their cursor on an object to have it read out the color. So for example, here you're seeing an image of peanut butter on a piece of toast, and the target on the app is on the peanut butter, and it's reading the color at the bottom of the screen as bold brown. And the app actually can also be used to simulate color blindness, which is a great way to get kind of behind what your students are doing and what they're seeing. And so the example on the right side of the screen is an image of a field of pumpkins. And if you have normative vision, you would probably not be able to see the pumpkins because it looks like just a giant green field because the orange is not coming through. And so it's simulating what that would be like to have that color blindness. And so what we did was when we looked at our first semester general chemistry curriculum, we anticipated that there were going to be several lab activities where students might need to use the app to make color-based observations. And those labs included flame tests, precipitation reactions, and titrations. So I'm going to share with you just kind of an overview of what those activities were and then how we use the app. And so the learning objectives for our flame test lab were to get students to learn how to collect flame color observations and identify metal ions such as sodium and strontium. So very classic application of a flame test. And the image that you're seeing on the right is a screen capture of the Beyond Labs laboratory. It's got a test tube stand, and the storeroom is where students can get the powdered metals that they would then be viewing in the flame test, or the powdered ions. And so there's a small window on the left-hand side of the simulation where a video appears of the flame when the students are collecting data in the lab. And so when we use the Colorblind Pale app in this lab, what I could do was I could anticipate with the simulation of color blindness what ions might be difficult for students to collect color observations. Then students could use the app in the lab. They could take a screen capture of the flame image and place the target on the screen. So you're seeing here an image of a sodium metal ion being burned in the flame test. And it's saying that it's a very faint orange color. And we got some feedback from a student who noted that the flame doesn't really stay the same color. and that the color names would kind of switch around as they were collecting the data. And then they said that for some of them, it stayed more one color than another, which is then what I went with when I was collecting my data, which for us was great news, because that's what students, what we wanted students to be doing as they were collecting data in the lab, of deciding this was the color presentation that I saw that occurred the longest, so it's going with that metal. The next lab where we applied the app was in the precipitations lab. In this lab, the learning objectives were to have students learn how to make observations about precipitation reactions, and then using solubility rules, writing net ionic and balanced chemical equations. And they were once again in that Beyond Labs general chemistry environment. And in this lab, what they could do was mix ionic solutions together and then observe whether a precipitate formed. So in that viewing window up in the upper left-hand corner, you're seeing a precipitate in a test tube. And so again, when we use the Colorblind Pale app, students could collect color observation data. So for example, here, the screen capture that I put on the slide is of a test tube that they were collecting data in the lab for. And in this reaction, it formed copper-2 carbonate. And what the app reads when the student centers it on the precipitate is that the color is a dull light blue. So that's a accurate observation that we would want students to be making in the lab. And then the last lab where we integrated the app was our titrations lab. And the learning objectives for this lab were to examine titration curves as representations of neutralization reaction processes, learning how to use a burette to perform a titration, and then calculating the exact concentration of a strong acid using a base of unknown concentration. So just your very typical strong acid, strong base titration. We had two types of titration activities in this lab, and they were both with hydrochloric acid and sodium hydroxide. In the first activity, students used a phenolphthalein indicator to do colorimetric titration. As a reminder, phenolphthalein is clear at low pHs, and then it turns pink and then magenta as we get over a pH of 7. And then in the second experiment, students were comparing colorimetric titrations with potentiometric titrations. So trying to differentiate between equivalence points and endpoints, and then interpreting the titration curve. So this is kind of first exposure to all of this for our students. And in this second activity, students were using a bromocresol green indicator, and that's yellow at low pHs and blue at high pHs. And so again, when we had students use the app, we were having them use it to look for when the color was changing, and the app allowed students to determine when the endpoint had been reached based on that color change. And so for example, in the image I have here, we've got a very classic titration setup. We've got the burette, we've got the stir plate, and a beaker on that stir plate with some hydrochloric acid in it that's being titrated. And the target in the Colorblind Pale app is placed on that beaker, and enough sodium hydroxide has been added that the app reads that the solution is a faint red color. So we've just reached the endpoint. And what the students could then do was figure out, okay, you know, how accurate is my colorimetric titration when I compare it to the titration curve. And so just to share some reflections on using this app, in our online laboratory course. The app integrated really well into the online environment. It can also be used in in-person labs. And there are actually more options available in the literature that I dropped down at the bottom of the slide here that you can use in the in-person lab. And those have more features such as they'll beep and things like that to indicate that the endpoint has been reached. And so as an instructor, the ability to simulate the perspective of students was extremely helpful for me. So I could start to consider what are multiple ways that we can have students collect data in the lab. And the research really bears that out, that incorporating multisensory approaches is useful to teaching chemistry for all learners. And so integrating more of these technologies really allow for that. And so some considerations for vision impairments in online laboratories. The online laboratory environment can be rather limiting for students with vision impairments, as they are often, those environments are often not screen reader accessible. And we need to provide text equivalents for graphics and contents that our students are supposed to be observing. As D'Agostino advises, our job as chemical educators is to create the least restricting learning environment for our vision impaired learners so that they can become independent learners. And we can do this by actively choosing accessible online lab environments and online lab or just online modalities as we start to integrate more of these simulations into our chemistry courses. So for example, instead of relying on what we really would call a mitigation measure, such as adding an app that like I did into the online lab environment, we can look towards simulations such as PhET out of the University of Colorado, which has integrated multiple accessibility features, such as adding alternative inputs and sonification to their simulations. And so I'm going to wrap up with, before I turn it over to Carrie, who is just so phenomenal. I'm so excited to be here with you, Carrie. I wanted to offer some general considerations for thinking about accessibility in online labs. I encourage all of you on this call to take the lead from Universal Design for Learning to actively work to prevent exclusion when you're designing your online lab materials. UDL encourages multiple means of engagements for students, so it really helps instructors to take responsibility for designing those accessible online labs so that students can convey their chemical knowledge and represent chemical content in multiple ways. And again, the research really backs us up that this is beneficial for all learners. And then I just really encourage you to be proactive in adapting new technologies for accessibility. As the disability advocate Meryl Evan urges us to really just aim for progress over perfection. Just getting started is very important because these technologies can improve your understanding of how students learn and really help your students feel included in chemistry. And so with that, I'm going to go ahead and stop sharing my screen, and Carrie, you can go ahead and take it away.
Thank you, Casey, very much. Let's start sharing my screen.
Oh, wait, I can't hear you very well, Carrie.
Moment. Share screen.
And Carrie, I think you need to move your video slightly to the, oh yeah, there you are.
No,
perfect.
I was totally in control with what I was doing.
Okay.
All right, good morning, everyone. It's a pleasure to be here today and co-presenting with Dr. Casey Wright from Western Michigan University. I'm going to take a slightly different angle from what Dr. Wright spoke about the low vision aspects and talk about more from the perspective of totally blind. Myself being totally blind had been since I was 7 years old. It sort of forced me to learn how to interact in the world as it is, not being able to see the printed word and to navigate from place to place without sight. And blind people, we are taught, well, hopefully taught, to learn how to read and write Braille, use access technologies such as text-to-speech screen readers. Some of the common ones are JAWS for Windows, VoiceOver on the Mac, TalkBack in the Android environment. Some of these are free, some of these are for pay. Use of a dog guide to get around or white cane, things of that sort. And then just methodologies to listen to the sounds of traffic in a city when you're crossing the street, or using the sun during the daytime to determine east versus west as you're walking in conjunction with time of day. And all of these non-visual ways of accessing information allows blind people to live more independent lives. Now, being blind, I'm also not aware of a lot of mass media visual information that's available in the print form or the visual form. And unfortunately, for blind students, there's an image of this poster floating around in our educational community that features this young child named Carol, who says she did not wear her safety goggles, now she doesn't need them, and it has a picture of her using a cane and reading Braille and other renditions of this picture. And I know this imagery was initially meant to be somewhat humorous, but used to scare teenagers to wear their safety goggles, because they don't typically like to do that. But there's a different meaning. There's a different meaning here, and that is, if you're blind, then maybe you can't do science, you can't be independent in the world, and it's contradictory to everything that I want to promote. So to that end, here's a second picture that shows a comparison. And this Carol poster, I think, hints at a deficit model of, okay, lacking vision means you lack ability to perform scientific exploration. And then on the right, there's a second picture. That's me in my younger days as a graduate student at Penn State University working in the research laboratory. And I share this picture because I want to say that it promotes what I call a pedagogy of possibility. It's like, it shows that a blind person can be independent, be an experimentalist working in the laboratory. The question is, how is that possible? Because many of you at this moment might be thinking, how can he work in the laboratory safely without injuring himself and others around him? So we're going to get into some of that. So first, we have a picture of one of my friends and colleagues, Dr. April Hill, at Metro State University in Denver, Colorado. And I met Dr. Hill years ago, back when she was a postdoc at Penn State while I was still in grad school. And she took an interest in wanting to know how to teach blind and vision impaired kids, how to do laboratory sciences independently. And so all of our working together has paid dividends, because here's a picture of her working with a blind student in an actual college level chemistry course with other non-visually impaired students. Okay. And this is the type of image that we want to make the norm rather than the exception to the rule. I don't know how many of you in the audience have had blind and vision impaired or BVI kids enrolled in your classes to date, but with this whole idea of inclusion and diversity, hopefully you'll have more opportunities to teach students of this sort. So then what are some of the tools? Some of the current tools are the SciVoice Talking Lab Quest, which is a product distributed and sold by Independent Science in the United States, along with Veneer Science Education in Beaverton, Oregon, to put a text-to-speech screen reader application on the handheld device. And once you have a talking data logger, all of the peripheral sensors that are compatible with that device suddenly talk. So here you have a picture of a temperature probe, but there's pH sensors, conductivity, balances, oxygen detection, you name it, we probably have a gas chromatograph, spectrophotometers, and they all work in different ways. Some of them you get actual spoken quantifiable data points. Others you get graphical information. So with the graphics, Dr. Wright mentioned the use of sonification in her remarks. And sonification, for those of you that may not know, is the use of an audible tone that changes the pitch changes with the slope of a line. So as the slope increases, the tone will increase, or as the slope decreases, it drops and hence will decrease in pitch. And if you sonify Cartesian graphs, say you've got the y equal x line, we all are intimately familiar with what that graphic looks like. It would sound something like this. Or if you reverse the graph, y equals negative x, it'll go, ooh. Okay. Or if it's the famous sine wave, it'll sound like a siren. Woo, 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 woo. So it gives you a really quick qualitative representation, non-visually, of what your graph looks like immediately upon the conclusion of your data collection. And of course, the talking lab quest, we call it the TLQ. It also has tabular information. You can access statistical information. And it's nice because it's got a small footprint, so you can use it in the laboratory, but you can also take it out into the field. This week, we have a field test of Talking Lab Quest. Excuse me? Oh, okay. And the field test is happening in Biosphere 2 in Tucson, Arizona this week. There's a blind researcher that's in a simulation of a moon colony, what it would be like to be a blind research scientist on the moon, and they're using the Talking Lab Quest literally this week to see how it would perform in that type of a sealed environment. So more to come on that in the near term. Now, besides the Talking Lab Quest, that gets you a lot of access, but it doesn't get you total access. So then we've got information here about a second device called the Submersible Audible Light Sensor, or SALS. And this was a prototype device that was initially developed at Penn State University with a senior design electrical engineering team back in the mid-2000s to detect the presence of a formation of a precipitate, the evolution of bubbles, the color change needed to be detected as part of an acid-base titration. So a lot of what Dr. Wright mentioned at her remarks using the color blind app, you can also do it totally non-visually with the SALS sensor. Well, I mention this now because after more than a decade of working with the American Printing House for the Blind, they have made the SALS commercially available to anyone who wants one. And it uses a mobile application called the SALS for an iPhone or an Android app. And then all of the audio tone outputs that you detect. So it uses the light sensor in that's submersible in a test tube or a beaker or flask. And then it uses ambient light, and it converts ambient light to audible tone. And so as your solution, say it's the iodine clock reaction, as your solution starts at the clear, it'll have a high tone, and as it goes from brown to darker colors to eventually black, the tone gradually drops. And the audible tone communicates to the blind student approximately when the color changes are occurring. And of course, we all know this is a chemical kinetics experiment, so your concentrations as you vary them with your starting materials will impact reaction rate. And as a result, the blind student can record time intervals by which the color changes are occurring with the SALS. So SALS is a wonderful thing. I recently talked to some colleagues at the American Chemical Society conference. They were excited to learn the SALS is now available because they feel when they do lecture demonstrations for sighted kids in a large audience, that if you're not seated in the first 4 or 5 rows of the audience, you're in essence blind to what's happening color change-wise on a bench top in the front of a large lecture hall. And they're going to start using the SALs in their lecture teaching. And the nice thing about the SAL, since it is an iOS or Android app, is if you have students in your audience that need assistive listening help, they can Bluetooth connect to the audio output through an iPad or your smartphone and hear all the audio tone nice and clearly. So those are the SALs. And then, so that's what we have today. A quick glimpse at what's to come. Recently, a grant was awarded to Independent Science to develop the next generation data collection tools for blind and vision impaired students. And we wanted to get more tactile graphic representation, refreshable braille. Now, refreshable braille is the ability to use a matrix of pin on a device that will make braille letters. And blind people have been limited to the refreshable braille technologies for decades, where it's limited you to one line of text. It works in conjunction with the text-to-speech screen reader program like JAWS or VoiceOver to represent the braille on the device. And right now I'm using one of these devices to give this presentation, and I'm looking at notes on my slides, but it's one line. Well, this SciDot product that we're calling internally is a multi-line refreshable braille device. So this one that you see in the picture is 4 lines, and it's 2 modules put together that shows 24 braille cells per line. This is a huge revolutionary innovation step forward for the blind community to have this much accessible refreshable braille in one time, in real time. Now, this is still prototype. This application here is using a prototype Android application to use a veneer sensor, one of their GoDirect sensors, to collect data via Bluetooth with this device. And it shows tabular information, but also graphical Cartesian graph in real time. So as your values are increasing, you can feel the graph increasing under your fingertips, or vice versa. If it's dropping, you can feel it. And you might say, why is that important? Well, if you take a moment to think, when you use computer-assisted apparatus to do laboratory science, what are your sighted students looking at on their computer screen once they hit the data collection? They're probably looking at the dynamic graphic forming on their screen, and it's cueing them as to whether or not there's a problem or if it's going as predicted. And so now blind and vision impaired kids will have that opportunity to do that in real time with this technology. So we're in the process of waiting for our review of our phase 2 proposal, which will provide the funding to assist Independent Science to take this product from prototype, as you see here, all the way to commercialization within the next 1 to 2 years. So we'll keep our fingers crossed, but that is a little glimpse of hopefully what's to come. So the methodology for accessible hands-on science learning for students with vision impairments does exist. The accessible laboratory procedures are needed. So when I say accessible, reading media is very important for blind people. I use Braille myself, so having access to Braille materials is helpful. Tactile graphics is simply a raised line representation of a graphic that I can feel. And then human reader, I mentioned that here. This is still important to us because a lot of text-to-speech screen reader tools, I use JAWS every day myself to do my work, but they have difficulty reading chemical expressions. So NaCl, it will read it as NaCl, or potassium hydroxide, it'll be CoA. And so it's not very conducive for high school and undergraduate students to learn chemicals or to do stoichiometry problems when you're reading your chemical symbology as words. So we need to come about with a new way of doing that. And obviously Braille, large print, high contrast representations of digital material, all is very helpful to this end, but the paradigm is shifting and we're moving forward into the future with more digital content, and hence needs to be more inclusive and accessible. So other tools here, I mentioned the side voice talking lamp quest, the submersible audible light sensor, and then we have to leverage all laboratory safety protocols. We strongly recommend those of the American Chemical Society, but there are others out there from other scientific organizations as well that are certainly qualified and valuable. But the whole idea of if you're blind, you don't need to wear safety goggles in laboratory is crazy, because a blind student, if chemicals get in their eyes, it'll still cause pain and discomfort as it would any other student. So blind students should be expected to wear proper safety equipment, lab coats, lab aprons, things of that sort. Be oriented to where the location of a safety shower is, emergency exits, how to use an eye wash, and those sorts of things, because you never know when an emergency might happen and who's responsible for who. I mean, it's easy to delegate that responsibility to a sighted buddy, but in the end, it's most important that everyone be able to take care of themselves if the unthinkable should happen. And then, of course, I mentioned benchtop management, knowing where you put objects in your laboratory workspace. We recommend that you use a cafeteria-style serving tray to serve as a tactile indicator on the benchtop to where spillable and breakable items might be placed. And if a blind student is working with a laboratory team, then they can they can agree on some basic conventions of putting anything that's spillable on the tray to serve as a tactile indicator. And we also found that putting extra beakers to support graduated cylinders so they're less toppleable is also a valuable technique. And then, of course, I have reference for mentorship for blind and otherwise students with other disabilities is also important. I had a blind mentor who was a professor who inspired me to stay on the path at points of frustration in my later years as an undergrad in Chem to keep going towards becoming a chemist. So mentorship is also very important. So the full integration of a blind student is a collaborative process. And as you see here, here's a picture of my friend, Dr. April Hill, again, working in a laboratory classroom with a BVI student, working with a pH sensor and some colored liquids and various beakers. This all was made possible not just by the faculty member knowing what is indeed possible, which is a key point, but also the university has a disability support services office that provides access to the curriculum, provides access to Braille materials, large print materials, and hard copy Braille digital form. So we as faculty don't necessarily have to know how to make the curriculum accessible in the physical form, but they're probably going to have a set of basic conventions you need to abide by to make sure the digital files are screen reader accessible as you create them, because it's much better to create accessible content at authoring stages as opposed to later as a mitigation. And I mentioned the Disability Services Office, but also the blind student themselves is a good resource for information for how they want to work in the laboratory, what they're comfortable with, what they're not. And the blindness skills, as I reference, commonly refer to Braille reading, access technologies, mobility, getting around using a white cane or dog guide. It really varies on the level of competencies these students have, whether or not they took the time to get comprehensive blindness skills training after graduation from high school or not. And based on those level of competencies of the quote unquote soft science or the soft skills will determine how comfortable they are in working in the laboratory. And I want to reiterate one other point. Not every blind student works the same way. So you may have blind student A this year that's very independent, and then blind student B next year, and they tend to be a little bit more of a traffic hazard in the classroom. So together, we can change the paradigm of what is possible for students who are blind or vision impaired. And back when I was in graduate school, Eric Wainmeyer is a blind mountaineer, and he summited Mount Everest in 2001. And his book, To Touch the Top of the World, came out shortly thereafter. And he taught me that as a blind student, that no summit is too high, nothing is impossible if we problem solve and figure out how to access visual information we can be whatever we want to be. And now the question is, how can everyone here help with this? And how the assistance we need is a lot of the science, education, technology, education companies, they're a lot of first to market, generate revenue mindset. And so they produce products that do really cool visual things and do wonderful tasks, and they rush to market. But there's this perception that blind and vision impaired and students with disabilities can't do science. So they don't consider us in their product development cycles. And as a result, you get lots of user interfaces with, say, science simulations and textbook, digital textbooks, and just mobile applications and other data collection analysis tools, which again do wonderful things, but they have limited, if any, accessibility capabilities for blind people and the use of their access technology. So I prepared this slide to show what are some questions you all here can ask your technology vendors. You know, what text-to-speech support does your products offer? Do you offer high contrast support? Can you support the production of tactile graphics and refreshable braille, among other outputs that maybe for some of you before today didn't know what all that was about? And I will say that when the customers in the field are asking the vendors to provide these capabilities for them, as sort of a stipulation for purchase or awarding of contract to a company, they tend to be more motivated. But other than that, you know, I've been asking and working with companies for years, and Vernier Science Education is sort of the leading entity in the science education and technology industry, in my opinion, today to take this lead. But as we all know, there are other companies out there that do similar, and we need to persuade them to go the rest of the way so that a hands-on science learning experience is indeed possible for blind students everywhere around the world. And with your assistance to ask these questions of your vendors, hopefully we'll shift that needle to move the paradigm forward to promote this diversity in an inclusion model of text-to-speech and accessible technology should be developed and provided. So, and with that, we have our acknowledgements. We'd like to thank our employers for the time and the resources to prepare our presentations today, and obviously the CLEAR 2023 organizers, and of course, the audience for your wonderful attention this morning. Thank you. I guess.
Right. So
are there questions?
Go ahead, Andreas.
Yes. Go ahead with the questions, please.
Yes. Thanks for this wonderful talk. There's pretty much of applause digitally here. And I think we have a question in the chat. I might read it out loud, but I'm not sure who's addressed with this question. So you just decide who starts answering, and then you move on maybe. So there's Jake Wainman asking, using a cafeteria type tray is such a simple, cheap, and easy to implement idea. Do you have any other recommendations of this style? Low-hanging fruit that anyone can do can have big impacts.
Another technique, we use needleless syringes, plastic syringes, to do volumetric measurements. Measuring specific volumes is very important, as we all know. And you can take like a triangle or a filer to put notches on the pull tab of the syringe to calibrate to specific volumes. So say you have a 50 milliliter syringe and a blind student needs to measure a 40 milliliter sample. So you just notch it at the 40 milliliter mark. So when the notch is aligned with the top edge of the cylinder of the syringe, then they know they've collected 40 milliliters in that syringe, is one example. But one of the risks with that is you need to make sure you have an excess of solution in your container where you're pulling your reagent from. Otherwise, you're going to pull air and you're not going to know that you've done that. So you need to make sure there's an excess. And another challenge is we all like to do micro scale experiments to minimize cost to our lab budgets. But everything that I shared with you this morning or today is all macro scale tools. So if your curriculum has micro scale processes or standards for a BVI child, at this point, we still need to stay on the macro, so you might need to scale everything for one station. But I hope to someday develop micro scale tools so that we can join you all on the micro scale. So. Is there another question?
Thanks. Yeah, Jake is answering in the chat. And I think if there are any questions, please just feel free to unmute yourself and also to show your video, and then you can ask orally also in your question. Otherwise, I had a tiny questions. We also worked like on including a blind student in the Chem lab here in Germany, Hanover. And also Andreas Schneider, I think the colleague from inorganic chemistry here. And how is so shifting also from the phenomenon-based level to the molecular level or submicroscopic level is something that is pretty just got a message from Nikita that I should move on, but pretty challenging for all students. So is there any tool that might help also like to support drawing conclusions from observations?
You're referring to visual observations?
Yeah, you have like the visual ones. And then we have to move on. Nikita just remind me. Thanks, Nikita.
Yes. Well, briefly, I mentioned the sound sensor that provides access to qualitative representation of visual information, and what Dr. Wright mentioned about the colorblind applications provide text. I don't know if there was spoken or visual text information about color information are great ways to access visual observation information.
Yeah, so maybe we can also keep in touch. I keep writing an email and can deepen this question maybe a little bit. So thank you again very much for this interesting talk, for keynote your time. And I think it really also opened up a really good framing for this topic of this year's CLEAR, like you had these pictures with the mountains and all the attitude we also that attitude that is involved when it comes to promote inclusive lab education. Okay, thanks so much. We move on with our next presentation.